we're talking about rigid body dynamics, and we ended last time talking about Euler's second law, the rotational dynamics, that turns into three first-order ordinary differential equations for the angular velocity. We're gonna kind of back up and talk about some other cases, because what we were mentioning last time was using the center of mass as the reference point. And you don't always want to use the center of mass. You might have a situation where you want to use a different point. So here's a situation. Suppose you are tasked with designing a jump. You have to design a car jump. So here's a car jump. And the car is kind of taking off from a ramp from the right, and then it's going to jump. And so there we go. So it's going from right to left. And you want to do the perfect jump. So the perfect jump means that as the car is in the air, it rotates just right to land at the same angle that it took off. So it ends up being a careful balance between the distance between the two ramps, the angle of the ramp at takeoff, and your speed. Because your rotation is all based on essentially the distance between the two tires. Because once the first tire is not connected to the ground, then you've got a moment due to gravity that's rotating this downward. So you need that rotation. I guess if we think of that as the pitch angle, you want the moment that's imparted during the time between the first wheel losing contact and the second wheel losing contact, and it'll be just due to gravity, but gravity with doing a moment with respect to this point that we're calling Q. So it'll be a moment, and then you'll also fly through the air, and hopefully halfway through be completely horizontal and then land. So there's some delicate balance there. Someone has to do the math to get this jump right. And I've got a video where someone got the jump right. I think. Here we go. Yeah. I don't know. There we go. Jumps and then lands very close to the angle of the ramp. And okay, it looks like the back tire went out, and like you don't want to just do that with your old clunker. But it worked out. So someone did the calculation and figured that out. Now, does it always work out like that? No. So here's another jump. Again, from right to left. Further jump. Something went wrong. Oh man, too much pitch. Okay, it was a stunt driver and he's okay, but it doesn't look pretty. So whoever he had on his team, I'd fire them. So this just gets to the point that, all right, you wouldn't want to look at the dynamics during this sort of takeoff phase using the reference point as the center of mass. You actually want to use this kind of bottom point of the tire, which is this moving point Q, right? Q is moving. We can assume during this time it's actually moving with a constant velocity. But we'll actually look at the case where you do the dynamics with respect to an arbitrary reference point, and that point could actually be accelerating. So let's just go into that. And like, where's this car thing coming from? So this is from, this is an image from your homework 3, which is now released and due in a week. So we're going to talk about rotation, about an arbitrary arbitrary reference point on the body. It doesn't even necessarily have to be on the body. But yeah, you could usually think of it as being on the body. And so what do we mean? It's that it's arbitrary. It's not the center of mass. It's not even inertially fixed. So that means it is possibly accelerating. Okay. And to kind of get the, to do this properly, we're going to go back to looking at the multi-particle collection and then just take the continuous limit. But I think things make more sense when we go back to the multi-particle collection. Okay. Let me insert figure here that I'm going to use. I don't know if it's any of these. Maybe I don't have it here. Or it didn't show up. All right. Well, I've got my, I'll just draw it. It's not too hard to draw. We've got the inertial frame, some origin O. We've got our particles. And there's going to be a center of mass, which might not be even located at any particular particle. It's just the center of mass point. So let's write what that is. Here's our center of mass point. And then we might have some other point that's convenient for some reason, some dynamical point Q. There doesn't even have to be a particle there, it's just a point. And we'll write the location of Q with respect to G. We could also think of location of Q with respect to O. And then there are particles, like there's particle I. So here is particle, the location of particle I with respect to Q. And then maybe we've also got location of particle I with respect to G, and so on. So we've chosen some point Q that's convenient for our calculation. And here's what we expect. We expect that the angular momentum of the collection of particles with respect to the point Q, so about the point Q, is going to be angular momentum with respect to the point G plus something. And we want to find out what that something is. So we first go back to the definition of what it means to be the angular momentum. The angular momentum of this collection of particles, it's going to be the sum, and let's say it's a particle collection of n particles. This equals the location of each particle with respect to Q cross the mass times the inertial velocity. And this is the inertial velocity of this VIQ. What is this thing? This is the inertial derivative of RIQ. Okay, so it looks like we're just doing a sum over R cross linear momentum, or R cross MV, but with respect to the point Q. And now we'll write that the location of each particle with respect to Q equals the location of each particle with respect to the center of mass, G, minus the location of Q with respect to G. So that's just from adding up these vectors, how they all line up. So we'll take that and then take the inertial derivative of it. And take a inertial derivative. We get that the inertial derivative of IQ equals inertial derivative of IG minus inertial derivative QG. Okay. And now we'll just substitute these things in, right? We're rewriting RIQ and we're rewriting VIQ in terms of some other things. So let's just substitute it in and then rewrite it. So over here, where I've got some room on the screen, we'll do it. So this is a sum from 1 to n, RIG minus RQG cross mass particle I, VIG minus VQG. Okay, and if you are following along, this is actually in page 260 of Kasdan and Paley. Okay, we've got this cross product thing. Let's just sort of carry through and simplify things. I'm gonna move this up. Sum from 1 to n, RIG cross MI, VIG. Okay, that's like the first term. And then minus sum 1 to n of do the mass times RIG cross IVQG. I moved the mass over because then you'll notice this summation is kind of on its own. The other part of the cross product doesn't participate in this. Plus, this is what the sum of the masses location with respect to the mass times the location with respect to the center of mass, which is, this is this thing we've been calling the center of mass corollary. So this is just 0 due to the center of mass corollary. And then we've got 2 other terms. So let me write those out. I guess we could first recognize what this is. This is just the angular momentum of the system with respect to G. Right? If you look up here to this boxed equation, if you just put in G instead of Q, you've got the definition of the angular momentum of the system with respect to G. So we've got that. But let's not forget those 2 other terms. So the 2 other terms are, well, we've got, we'll have RQG, and RQG doesn't have a subscript I, so it's not going to participate in the summation. We could pull it out of the summation. RQG times sum from, I goes from 1 to n. Actually, there's a cross product here, cross MI, the velocity IG. Now, this thing also equals 0 because it's just the time derivative of, let me put this thing in orange parentheses over here. If you take the inertial time derivative of that thing in orange parentheses, you get this thing that's in the parentheses. So it's basically the time derivative of 0. So that's also 0. And we'll say, again, due to the center of mass corollary. Plus, now what? I think we can actually pull out some of the masses times, and it's a negative times a negative, which gives us a positive. RQG G cross I V Q G. It's inertial derivative there. This sum of masses is just the total mass, which we've written as mg. It's like the mass of the center of mass. So just collecting the terms that aren't zero, we get that. Remember what we were looking for? It's this thing up here in the upper right. We wanted IHQ equals IHG plus something, and that's exactly what we get. What is that something? It's the total mass times this location of the point Q with respect to the center of mass cross the inertial derivative of that position. This doesn't have a name. It's just a way of writing the for a collection of particles, right? The angular momentum with respect to some arbitrary point. When you get the arbitrary point, you pick up this other term here. So angular momentum with respect to Q is angular momentum with respect to G plus some stuff related to the displacement of Q from G and the total mass. The real power in writing things this way is when you now take the inertial derivative and get the what is the rate of change of the angular momentum with respect to Q. So we take an inertial derivative. And then this equals, so on the right-hand side, we take an inertial derivative of that first term plus an inertial derivative of the second term. And then we can just carry through. We've written a formula before for what the inertial derivative of the angular momentum about the center of mass is. That's going to be related to moments about the center of mass. But this second thing with this cross product, what do we get there? Well, you could pull out mg. Mg's not, we're saying the total mass doesn't change in time. So pull that out. And then we've got inertial derivative of RQG cross I EQG. I mean, this thing just is the definition of that inertial derivative. So you have the a vector cross itself, so that's 0 plus mg, and now the derivative acts on the other side, right? This is it's like a product rule for cross products. Take the derivative of the first thing, then plus derivative of the second thing. Derivative of this. What is this? This is the inertial acceleration of Q with respect to the center of mass. And we could also write that as that's the inertial acceleration of Q with respect to the inertial origin O minus acceleration of G with respect to the inertial origin O. Then let's write this all again. Got this derivative of HG minus, and I'll write things this way, RQ minus RQG cross mg acceleration of G plus RQG, that's a Q, QG cross the total mass inertial acceleration of Q with respect to O. All right. And now what? Well, we know that the way that this changes in time is equal to, at least we wrote this before, it's the sum from 1 to n of the moment arm, so location of each particle with respect to the center of mass, cross the force, just due to external force, nothing internal between particles because of that internal moment assumption. What about this? This is mass times the acceleration of the center of mass. Here we use the superparticle theorem, and it says that it's like mass times acceleration equals total force. The total force on this collection of particles is the sum of the external force. And then we've got something over here that looks like we expect R cross something that has units of force. So this does have units of force. We're just going to call it the inertial force. It's like a fictitious force due to the inertial acceleration of the point Q. So we can call that, it's just due to an inertia and related to our choice of point. So it's due to the acceleration of Q. Okay. Got a big expression here. So total inertial derivative of the angular momentum of the system about Q equals, and you'll notice we've got this force sum over external forces. And so we could actually have an overall summation here, 1 to n RIG minus RQG cross the external force on that particle plus RQG cross, we don't have anything else to call this except mass times the acceleration of the point Q. All right, this subtraction of these two vectors is the location of particle I with respect to Q. So then we will define, we're going to define the moment of the system about the point Q as this sum from 1 to n, the moment arm, but now with respect to this point Q, RIQ cross the external force. And then what are we left with? So here is the evolution equation for IHQ. It's the total moment of the system about Q plus an extra apparent moment just due to the acceleration of Q. And in the book, this is equation 717. It's also equation 930. It gets shown again. Okay. So how do we interpret this? This is, in some sense, it's a more general rotational dynamics equation because it doesn't depend on using the center of mass as your reference point. You can use any reference point as long as you're careful about things and you take into account the acceleration of your point Q. There's also this fact that the moment about Q is equal to the moment about the point G minus R Q G cross, and I'll just write this sum of the total force. This is, the book calls this the moment transport theorem. And it takes maybe one more line to convince yourself of it, but I don't want to show that. So this is sometimes useful. It relates the moment about the point Q with the moment about the point G and the displacement between Q and G. So, like I said, view this as it's a more general rotational dynamics equation. We've written it in terms of summations as if it's for a multi-particle system. If you replace summations with integrals, it all carries over to a continuous mass distribution. Okay. But then it's all still true. In fact, starting up here, this equation up here holds for a continuous mass distribution just as well as a discrete one. So a continuous mass distribution, we usually mean a rigid body. We don't mean something squishy, like a squishy blob of goo. We typically have in mind some rigid body situation. So let me draw rigid my arbitrary rigid body. Here's the arbitrary rigid body. Here's a inertial frame with an inertial origin O. And I don't know, there's a center of mass somewhere. Here's a center of mass. Here's our point Q. So this is R, Q, G, it's the vector from G to Q. So where is Q with respect to G? We'll be summing over, this is a 3D distribution. So here's our volume element, I'll call it dV. And we've got the location of each of these volume elements with respect to Q. So dV slash Q. Inside here, we've got a density. We'll write this as the density at this location, dV slash Q. Each little piece could be, it has some inertial velocity. So here's the inertial velocity, dV Q. It's just the inertial derivative of this blue vector. And then we'll also have a force. Running out of things, how about a force? I'm running it as little f. It's little f. It's the force density. So it's force per unit mass on this little volume element. And how does all this come into play? So for a continuous mass distribution, mq, total moment, is defined to be an integral over the body. So if I didn't write it over here, fancy B tells us we've got the body. It's integral over the body, R dV, with respect to Q. So the moment arm cross the force density times the mass of this volume element, which means that's the density times dV, the little infinitesimal volume element. This thing, we'll call it the force density. It is the force per unit mass. And we're not thinking of, different parts of the blob have a force due to each other. So this is a force due to just something external to the whole system. And this also equals the moment due to the moment transport theorem, this thing here closer to the top. This equals if you were to write the same moment, but about the point G, the center of mass, minus RQ G, cross the total external force. So the total external force is just a integral over the body, this force density times the mass density dV. We're just trying to add up the contribution due to the force density all over the place. So the force might not be uniformly affecting things. All right. So sometimes we write this F ext as just F sub G, or just F. So maybe we say also known as. Okay. And this, I think, is in, I don't know why the book puts things in a different order, but I don't like its order. So this was back in chapter 6. Okay, so that's the total moment about an arbitrary point. We also need the total angular momentum about that point. So the total angular momentum about that point, you could also write in terms of an integral of the, it's R cross the mass times the velocity, but we'll write the velocity here first, and then the density. Because density times volume gives us the mass of that little volume element. So we know it can be written that way, but what we will typically do is once you've chosen some body fixed frame, B, then you will write this as equaling the 3×3 moment of inertia matrix of the body with respect to Q times the angular velocity of the B frame with respect to the I frame. So there's some frame, there are some directions fixed in the body. I don't know what they are. Ooh, this is kind of, I didn't mean to do that. Too thick of a line. There's some frame that's attached to the body. And so there's some angular velocity that describes how the body is instantaneously rotating with respect to the inertial frame. All right. So, and if you want the relationship of the moment of inertia with respect to some arbitrary point and the moment of inertia with respect to the center of mass, like maybe this is some standard shape where you could look up in a table what the moment of inertia is, and it'll usually give it with respect to the center of mass. So that the relationship between these two is given by the 3D parallel axis theorem. So I'll just write this here for good measure. So it says moment of inertia with respect to Q is moment of inertia with respect to G plus something. And we know what that something is. It's going to be related to the vector of Q with respect to G. In fact, maybe I'll just write that in red because I wrote it in red up there. R, Q, G. Magnitude of that squared times the 3x3 identity matrix. That's what this giant one is. Minus R, Q, G with respect to the B frame. R, Q, G with respect to the B frame transpose. So where we've written R, Q, G with respect to the B frame as a column vector, so then this thing on the right-hand side works out to be a 3x3 matrix. Okay, that's a lot. That's a lot of theory. It's good to know. So how might we use this? Well, there's the cart in a pendulum system. So just to sketch out some scenarios. Here's a cart that maybe moves only, horizontally, and you've got a pendulum, so just some rigid rod attached by a hinge joint or hinge joint. Well, that joint is going to be moving arbitrarily because maybe we've got a remote control and we're moving the cart, or we've got some control system. So the pivot point Q moves. And we know that for a pendulum, so there's the center of mass of a pendulum, there's going to be some moment due to gravity. And so if you were to write the dynamics of the pendulum, just the pendulum, you would want to write it with respect to the pivot, the dynamics of this system with respect to the pivot, but the pivot is moving and possibly accelerating. So you would have to take that into account. Another case is this jumping off of the car. So here's the car. And you'll want to use this reference point down here, this contact point, and figure out what is this vector. I guess you actually want to know the opposite vector. What is the location of Q with respect to G? So here's that point. You want to get Q with respect to G because that's what enters in the dynamics. And there would be a moment due to gravity acting at the center of mass. So there'll be some moment. And over here, for this cart pendulum system, the acceleration of the point Q with respect to some inertial origin. Here's some, inertial origin. This thing is going to be non-zero because maybe the cart's moving back and forth and whatnot. Over here, you can assume that the point Q is moving in a constant velocity. So this thing we're saying is zero because the inertial velocity of Q is v. Let's call this the v vector. And this is a constant, at least over the time that you're leaving the ramp. It's a constant vector in direction and location. You might say, oh, but this it'll tip down a little bit. Yeah, that's a small effect. So you can assume this. Okay. Which brings up that yes, there are special cases to this. Where's the main ODE? The main ODE is this guy here, which I'll just highlight in yellow. So let's look at that. Okay, there's a special case. There's two special cases. If Q is not accelerating, then this part, this is 0. So that second term goes away. There's another way the second term can go away, which is if Q equals G. So if you happen to use G as your reference point, then RQG is the 0 vector, and that goes away. So the two special cases where this reduces to something simpler are, let's see, if the acceleration of Q is 0, this is a 0 vector. If the acceleration of Q is 0, then we have that the inertial derivative of angular momentum of the system is just the moment with respect to Q. The other case is if Q equals G, that means that RQG is the 0 vector. So that second term also goes away. And we're just back to what we already knew. This is the basically using the center of mass as the reference point. Okay. So we get that. All right, it's about 10:15. I want to talk about, this is some heady stuff, and trying to tackle the 3D things head on. It's maybe difficult. So we'll start with looking at just planar rigid body motion. I've given the theory that works for 3D, but now let's reduce to just planar rigid body motion, because that is the easier thing to deal with. This car situation falls in that category. The cart pendulum would fall into that category. We need to take that step before we go to full 3D rigid body motion. So we will look at the special case of planar rigid body motion. And this is what chapter 9 of the book talks about. So it's, you know, another special case. What are the assumptions that go into this? When can you do this? You assume that all motion stays in a plane. So and maybe it's kind of an art. Maybe you're thinking that car jumping, it looks like a lot of 3D stuff was going on. Well, the motion was, most of the motion was just happening in a plane. Don't think of little lateral wobbles. Most of the motion was in a plane, okay? Here's another one. We've got, for the rotation of the rigid body, so here's some kind of arbitrary rigid body. Rotation, is about a single axis. And that would be kind of normal to the plane. And that basically means that you only need one angle is needed to describe the rotational motion. So maybe it's like if I have some body fixed frame here, then with respect to some inertial frame, I only need one angle, like this angle. One angle is needed, okay? If we have this situation for planar rigid body motion, then the ever confusing three-dimensional angular velocity vector becomes just an angular velocity scalar with the axis that's B3. So we only need to deal with a single scalar component. Maybe I'll draw a different arbitrary rigid body over here and more carefully write, here's, let's use the center of mass as our origin here. Here's some inertial directions. And then we've got some body fixed directions. Maybe these are principal axes, or maybe we just randomly chose some body fixed frame. So here is B1, B2 direction. We would use this angle between E1 and B2 as our angle. And then we've got a unit vector that's coming out of the screen at you, B3, that equals E3. And maybe I've got some also an arbitrary point Q. Maybe I would need that. I don't know. But it's a big simplification because when you have planar rigid body motion, instead of needing, maybe you don't yet know why, but in general, you would need three angles to describe the orientation of something like this coffee mug in three-dimensional space. But if it's just sort of moving laterally, then all I need is one angle. You're like, oh no, don't tip it too far, you spill your coffee. Yeah, I don't want to do that. All right. When we write the angular momentum, in general, this equaled some 3×3 matrix times I omega B as a matrix. But now we just have the only component that matters is IHG in the B3 direction. This is IG is now a scalar. It's not a 3×3 matrix, just a scalar times I omega B, a scalar in the B3 direction. So you don't even have to worry about all the other things. So if I were to write what is IGB, the full 3×3 matrix for this thing, it's a bunch of components we don't now care about anymore. All that we care about is what we called the 3,3 entry before, but now it's IG. So I33 is IG. It's the only one that we care about. So that's nice. We went from a 3×3 matrix to just one number. The Beatles said love is all you need, but IG is all you need. The rigid body kinematics becomes quite simple. Maybe I'll put it up here. The rigid body kinematics ODE. Right now that we've got this angle, it's d theta dt, so theta dot, is equal to I omega B, scalar. Scalar ODE. We don't have a set of three or whatever, we've got just one. So big simplification. The parallel axis theorem, usually that's what you learn in sophomore level dynamics. You learn the parallel axis theorem in 2D. And again, big simplification. So if I wanted to use my reference point Q, or just some other point that's not G, IQ equals IG plus the mass of G, and then the magnitude of, basically it's just the distance between Q and G squared. And this is equation 9.34. This is kind of an aside, but maybe not really. You need to think about what are the dimensions? What are the dimensions? What are the units of moment of inertia? Remember, the moment of inertia kind of plays the role of mass, but for rotational dynamics. So mass, what are the dimensions of mass? Well, it's mass. It's kind of a fundamental dimension. The dimensions of moment of inertia are length squared times mass. And sometimes people, books, studies, engineers will use what they call a radius of gyration. It's another way of writing what that length is. So if we have some body and it's got about the point Q, we've got the moment of inertia. They'll write the moment of inertia as K sub Q squared, where K sub Q has units of length. And then this would be times mg. So KQ square root IQ over mg. The radius of gyration about Q. And so of course, if you have as your reference point the center of mass, then it's IG over mg. You take the square root of that. This is going to be some length. So this would be radius gyration about G. Often you can guess, you can get within an order of magnitude of what the radius of gyration for some object is. So remember, we're just thinking of planar stuff. If I've got some object and I just sort of estimate its length, I'll say, well, it's sort of got a dimension from one side to the other of L. So L is a length scale of the body. So for like humans, our length scale is about a meter, okay? Then the radius of gyration about any point is going to be some non-dimensional number alpha times L. So this non-dimensional number is, usually close to 1. Within an order of magnitude. So if someone said, quickly estimate the radius of gyration for a car, well, okay, if you got to do this right now, I'd say, well, a car, I don't know, L is about 3 meters. I don't know what the mass is. I think it's about a ton. I don't know, 10 to the 3 kilograms. So then I could pretty easily estimate what the moment of inertia for a car is, kind of about its center of mass. It's going to be on the order of 10 to the 3 kilograms times, what's 3 squared? We'll say 3 squared is 10, about 10 meters squared. So, okay, 10 to the 4 kilogram meters squared for a car. A car, not a care. Some things are easier to estimate than others. Moment of inertia, just, you know, order of magnitude. I think it'd be cool to have a whole class called order of magnitude physics for engineers, but I got other things I'm doing. All right. So now rigid body dynamic, this is kind of a side, like I said. I do use in one of the homework problems, I mentioned the radius of gyration, so I figured I should put it in here. What about rigid body dynamics in 2D? Well, here's the inertial derivative of, and we'll use, you know, center of mass as our reference point. You can do the same thing for some other point if you wanted. So we know that this is IG as a scalar times I omega B as a scalar. And we can actually pull out either B3 or E3. It's an inertial direction. So the time rate of change of directions doesn't affect anything now. So this is going to be, and IG won't change. So all we're left with is IG times I omega B dot. And what is I omega B? This is just I omega B dot is rate of change. Well, we don't even need that inertial thing anymore. Just the time rate of change of d by dt of theta dot, since I omega B is theta dot. So this equals IG theta double dot 3. Mg is going to be Mg a scalar in the third direction. So you're left with probably something that is familiar from sophomore dynamics. It just becomes, we'll write it this way, IG theta double dots, the inertial, the angular acceleration, Mg, right? Only the E3, or which is the same as the B3 component, matters. You could then rewrite this as the angular acceleration equals IG over Mg. So we have a second order ODE for the angular coordinate. The only angular coordinate. Now, and IG is a constant. So IG is a constant, but Mg might change. Mg might be a function of theta or theta dot or both. I don't know. So this ODE still might be kind of complicated. But there it is. There it is. So this will get you through that homework. The problem related to the jumping car. And I will mention the homework at the end. So yes, looking at rigid bodies in 2D is a big simplification. Another way to think of it is in terms of degrees of freedom. So for rigid bodies in 2D, I mean in 2D, only have 3 degrees of freedom. What do I mean? So if I have some rigid body, and let's say I'm tracking where the center of mass is with respect to some inertial origin, writing where the center of mass is, that's just given by 2 numbers. Maybe think of it as x and y, x and y. So I've got 2 translational degrees of freedom. And then if I'm tracking the orientation of this with respect to, say, the horizontal direction, so then I've got 1 angle. So that means I have 1 rotational degree of freedom, that angle. So 3 total degrees of freedom. In 3D, I end up having 6 degrees of freedom. So if I'm looking at a problem and I can use this planar rigid body dynamics or rigid body dynamics in 2D assumption, it's a savings of half of my degrees of freedom. So it's easier to simulate, model, and all that. So if you do end up tackling a problem or a new problem for your research or work, it might be good to start with a situation where you can make the rigid body in 2D assumption just to make sure you understand that and then move to 3D. Okay. I wanted to say something else that's related to planar rigid bodies. This is now, what I mean here is now thin rigid bodies. So they're sometimes called plates. So planar rigid bodies in 3D. And so this means, thin or flat plate. So many objects that you deal with can be approximated as having a thin dimension. A thin dimension. And here by thin, that just means that it's negligible. And just for clarity, we take the thin dimension to be along B3. So the Z coordinate. That means that the body is in the B1, B2 plane. So X and Y. So here is this is not a very good sketch, but here is a sketch of this is like a flat plate, rectangular plate. So this dimension here, this is the thin, it's a thin dimension. So this is our body, B, and we've got let me write the center of mass here. And then B3 is normal to the body. And then I've got B1 and B2. So the body is in the B1, B2 plane. If I have this situation then what happens to, there's something that happens to the moment of inertia matrix. So here is that moment of inertia formula. And we're assuming here, we pulled out the density. So let's assume this is, it's got uniform density. Then if we have the, if the z direction, right, this just goes to 0. So anywhere that we have z, we can neglect that. If you were to take the integral, that component will be 0. So this goes to 0, 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 this goes to 0. Just to remind you, what is this? I'm just rewriting equation 11.22, but now showing things that go away. So what will we be left with? We'll be left with I11, I12, and then, and this is a symmetric matrix. I'll get I22, I33, and the rest of these are zeros. We also have the case, if you look at it in terms of integrals, I33 equals I11 plus I22. So there's a relationship between that, the moment of inertia for rotation about the B3 axis, the axis, here's something that's kind of like a flat plate. Kind of like a flat plate. So I've got this normal. So I33 equals I11 rotation about that plus I22. And yeah, I guess it's worth noting that we've got some zeros there. So what does that mean? You know, I3 equals I3, I equals 0. For I equals 1 and 2. So this is the big one. So you can assume this if you've got some kind of body. So for example, a flat plate like this coaster. This coaster is thin. It's got a thin dimension. So I'll say, well, it's so thin, it's basically negligible. It's not going to contribute anything to that dimension will not contribute anything. So this is a flat disk. It's got a mass m, a radius r. So here's a flat disk. There's our center of mass. Here is B3. B3 has to be normal to the plane of the object. And then B1 and B2. This has a radius r, a mass m, total mass m. And you could do the integral to find out what the moment of inertia is, but you could also just look it up. Somebody's done it. It's probably in Appendix D of the book. What you'll find is that I11, so that means taking the disk and trying to rotate it about, right? Since this has rotational symmetry, there's no difference between the B1 direction and the B2 direction. So due to rotational symmetry, I11 is actually the same as I22. And it turns out to be 1/4 mr squared. Right, what would I have guessed? I would have guessed, well, or to order of magnitude, this thing from side to side is 2r, and it's got a mass m. So I'd say it's going to be on the order of 4r squared times m. And okay, I'd be off by an order of magnitude. That also means I'm within an order of magnitude. So this is due to rotational symmetry. When you do it carefully, you get this 1/4 factor. And then I know from this formula up here for planar rigid bodies, things that have a thin dimension, I33 is going to be I11 plus I22. Those are equal, so this is going to be 1/2 mr squared. So what does that mean? Technically, it means it's twice as hard, should be twice as hard for me to rotate this about that B3 axis than it is to rotate it about any axis that's kind of going through the body. And it's probably not noticeable on something small like this, but on some kind of heavier thing, like a the sewer covers, manhole cover, you know, good luck picking that thing up, and then, you know, good luck trying to rotate it. Apparently it's easier to rotate it this way, and you could experimentally verify that. So it's twice as hard to rotate a flat disk about its axis. Its axis of symmetry, I mean, basically the direction normal to it. This is as compared with about any axis in the plane of the body. Passing through its center. So where might this become useful? I mean, what if you had to calculate something for a triangle? Well, you know where the center of mass is now because we actually did that calculation. It's 1/3 of the way. This is a flat plate, triangular plate, right triangular plate. And if you were to calculate, you could calculate the moment of inertia for that. And if you did that, you would get something for I11 and I12, actually I22. You'd actually get an I12 that's not 0 if you used directions that are just kind of the main ones you would use, something along that's perpendicular to the bottom and something perpendicular to the top. That's an easy natural choice. But B1 and B2 here are not the principal axes. For the disk, any two orthogonal directions in the plane of it are principal axes. But for the triangle, there are some special directions, and you could get them from the eigenvalues, and this will be offset by some angle, and these would be the principal directions. I don't know what we want to call them. Maybe we'll call them P1 and P2. So there's principal axis directions are not equal to B1 and B2. What does that mean? If you had a triangular plate, and we haven't yet got to the kind of details about how this works, but you could not get pure rotation. If you had this in the space station and tried to get it rotated, a flat plate triangle will not rotate purely around B1 or B2. It will about this P1 direction and this P2 direction. And of course, the B3 direction is going to be, so coming out of the screen, you could get it rotating about that. That is a principal axis direction.